So as a quick reminder again, our naming assessment is up. Please make sure you start taking a look at that. Second, also, is there some videos to help you review how we do IUPAC naming in different ways. This is something that definitely go take a look at it, review through. These are tutorials that were prepared by Professor Johnson. Really, really, really excellent sort of sequential thing. So quick show of hands, who in high school or anything previous has done some kind of IUPAC naming before? Some could, okay, good. Who's done the goal, or like have you ever picked up like a wrapper of some food or like cleaning products, looked at the back of it, and you see sort of this alphabetical, like, oh, this is made with 2-lauryl sulfate or 4-ethyl-2-butanol or anything like that. If you were familiar with that kind of lexicon of talking about molecules, yes? This is basically what we're doing here. This is, again, back to the idea that organic chemistry is like grammar, like syntax. The first thing about IUPAC naming, and the goal of IUPAC naming of what we're doing here, is to provide a common language where an IUPAC named molecule, as written, corresponds to one and only one structure. Okay? So the concept is, and this is something I want to emphasize, the goal we have with IUPAC naming is to come up with a common language. Please, 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 do not focus on IUPAC so much that in 3 weeks from now, if you're coming up to me in, let's say, office hours, and, okay, is this a 2-methyl-3-ethyl, or is this a 2-fluor? No, not the concept. The reason I mention this is IUPAC naming is this really nice systematized thing that feels really compelling, very important, not important for organic chemistry. And I'll show you a couple examples around this now. We have to get this right, but the problem I see every year is students will come into IUPAC. It feels so fun to play this puzzle that 3 weeks from now you're focusing on IUPAC and we're talking about chemical bonding and reactivity and geometry and chirality, and you're still focused on IUPAC. So move through this point and let's continue on. That's all I'm trying to emphasize. Do not get baited into the trap that this is like the best version of Wordle that you've ever played. So we talked last time about the proper way to draw things and how we draw things mean things. This is a structure that is apparently supposed to be condensed structure shown up there, CH3, CH2, CH3. And I've decided to draw it this way. What are the things you see that are wrong about this drawing? Yeah?
A lot of extra H's on the drawing.
There's a lot of extra H's on the drawing. How? Where would you say there's extra H's?
At the end of the stick.
Yeah, like the end of the sticks. Oh, that hurts. But yes.
I'm sorry.
These here, what if I draw this, a line sticking out to space, what am I telling you? What does that mean?
CH3.
It's a carbon with 3 hydrogens. So this here, these are all carbons. Absolutely. That's wrong. What else? There's something else that I do not like about how this is drawn. Sorry, say that again? Yeah, you're specifically, in this case, you are drawing carbon, carbon, carbon. When you're doing line bond structure, that is so you do not have to draw carbon, carbon, carbon. So you do not, or we call this the implicit hydrogen rule, or again, this carbon rule means lines at a junction are a carbon by default. You do not have to call these as carbon. There's one more thing that I really don't like about this. What else?
So that it's a line on the same plane as their zigzag.
Exactly. Now, as this is drawn, we mean, like, when we go to line bond structure, we're beginning to represent a 3-dimensional molecule in a 2-dimensional plane, which means the geometry of the atoms, their hybridization, should be somewhat reflected here. If I was to physically build this molecule, it is not a pancake, like taking a bug and squishing it flat, right? That's why you get, this molecule would look like a bent structure, right? It's got this kind of zigzag shape because we're trying to show that carbons, sp3 carbons, are what geometry? sp3 is tetrahedral. sp2 is, and sp is, absolutely. The shape matters. So what we're trying to emphasize is this molecule. So the structure I have here, CH3, CH2, CH3, that's all I have to draw. But it's a good day, so I'm going to draw it like this. Lone pair. No. But what point is, all you need is 2 lines in a sort of a zigzag type pattern, and we're trying to emphasize that there are 3 carbons in a line in the plane of the page. I do not need to draw anything else. If I want to get really creative, I could draw the hydrogens. One way up from this could be CH3, CH3, and I'm going to draw these explicitly like that, right? Why did I do this? If you look here at this end, that is written CH3. I've decided to draw this one as H3C. Why did I do that? Yes? Exactly. I'm trying to talk about what atoms are connected to what atoms. So over here, although this is a CH3, because I have this bond and to this point, if I were to draw that as CH3 line CH3, I'm almost saying right here that there are 3 hydrogens which are connected to the carbon adjacent to it. So you usually will invert the order. If this was an oxygen, I might draw on one side OH, but if it was pointing the other way, convention would say HO line. I'm trying to emphasize that the bond is to the oxygen and the carbon, not the hydrogen in between the two, right? So this is, again, syntax. These are smaller things where, another thing about drawing, too, just like language, there are regional dialects. So what I'm teaching you is how I learned. This is my syntax. This is my regional dialect. Depending on where you go, if you go to Oxford, there's certain other rules about small details like this. So this is also where if somebody draws something, I can be like, ah, yeah, you're from one of those dirty British schools. Yeah, that's definitely what's going on. So again, they're just things to pay attention to. So sometimes, as you do interact with other parts, they're not sometimes wrong. What you'll see is small changes in drawing convention. But these are the major rules that I always play. Okay, look at this structure. And please, take a second. I want you, first of all, really quietly, come up with an answer in your mind. We'll give that one 30 seconds. Okay, now, I want you to turn to the person next to you and convince them why you're right and they're wrong. How many hydrogens are shown here? Okay. Now that we have consensus, everybody all together, the answer is 14. I agree with you. Question? No? Okay. Where did you, if you were looking on here, who did not get it right the first time? It's okay, no shame. What did you miss? Where were the carbons that you said, ah, I forgot that one? So quickly, which one did you miss? The one with the double bond. Yeah, so right here. Yeah, okay, that's a good one. That's a very common one, right? And there's only one there. Why? What is the hybridization of that carbon? That is a... The shape is trigonoplanar. The hybridization is sp. Yeah, that's right. There's only one other hydrogen necessary to fill its valence. Okay, where else? Where somebody else missed one? Was that the one for everybody that missed one? Which one? This one here?
Sorry, the one top.
Ah, yeah, yeah. How many hydrogens right there?
0.
Yeah, goose egg. There are no more hydrogens. Same thing here. How many?
0.
None needed, right? 4 bonds are shown as either double bonds or other components, right? Oxygen, no hydrogens needed because what is the valence of oxygen? Normal valence is 2, right? How many lone pairs on oxygen? Yeah, there's 2. Yeah, we'll get to that formal part, but that's it. The other thing, too, is, again, 1 at this center. These are common things that you'll see, and this is what you need to program yourself into, is when you see drawings like this, you can look for those sorts of points. Okay, so that's how we do implicit hydrogen rule. That's how we look at line bonds. Now, the important thing about line bond, though, is it's representing the shape, structure, hybridization, But it doesn't sometimes, there's conformational flexibility, ways you can draw things that do mean the same thing, and some ways we draw things that mean different things. These are what we call constitutional isomers. Constitutional isomers mean structures or molecules that have the same formula but different bonding. So the same molecule, for example, is this my right or left hand?
Right.
There you go, right hand. Is this my right or left hand?
Right.
Right or left hand?
Right.
These are the same molecule in different presentations. So I can draw it showing, pointing this way, pointing this way, pointing this way, same molecule. Right or left hand? Right or left hand?
Right.
These are isomers of each other, made up the same stuff, but physically different with different properties and capabilities. So here we have at the bottom 3 molecules. All of them have the same formula, same number of carbons, hydrogens, and oxygens, right? And you can count them off. They should all have the same formula, C5H10O. But they have very different densities. They have very different melting points, completely different chemistry. If I asked you guys to rank these, which one of these would you eat? So guys that are in the number 1 camp, 1 is safe to eat. Well, 2 is safe to eat. 3 is safe to eat. Yeah, I'd go for that too. It turns out molecules like this, these tetrahydropyranes, they're very common. They actually come into artificial, like there's molecules that are similar to this that actually smell like buttered popcorn. So yeah, these ones are ones that are actually additives. This guy here, pentanones and stuff, your body, is anybody diabetic or know somebody who's diabetic? Have you ever heard something about it being ketonic, like keto diet? Yeah? Ketones. These molecules and ketone bodies like this are common if you're burning lipids in your body. So you can build these up very frequently. I'm not saying, okay, backstory. Do not drink any of these. But if I had to rank these, this is the guy that makes me worried. Molecules like this, these alkene alcohol ones, they're ones that do a lot of bad things to you. But see, common in biology, sort of common in biology too. Anyway, point is, all we're doing is rearranging where those bonds go. Okay? These are constitutional isomers. What that means is physically different bonding character. You have to move those bonds around. What about these? What is their relationship to each other? Are they constitutional isomers? Same molecule, different formula. Are they identical, or they have nothing to do with each other? So, who's in the constitutional isomer camp? Constitutional isomers. Okay? Identical. They're the same molecule. And they have nothing to do with each other. They are actually identical. So here, look at this way. How did you come to that decision? First of all, look at their content. How many carbons in both of those structures? Yeah, they're both 6. 1, 2, 3, 4, 5, 6. So again, numbering those off. There are 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. How many hydrogens in both of these? 3, 2, 2, 2, 2, 3. There are 14, right? In both cases. What makes them different, though? Well, nothing makes them chemically different. That's true. How they are presented is different. This is my right hand and my right hand. These are just looking at the same molecule in different orientations. The difference between these is how the molecule sits. These are what are called alkanes. We'll get into that in a second, but they're floppy little molecules. Single bonds can rotate. Nothing changes about this molecule just by doing a rotation. It's just a different presentation. It's like picking up a noodle and stretching it out straight versus taking that same noodle and flopping it around in a circle. Same molecule. I didn't have to break anything about it. I don't have to change any bonding. Yes?
Are the carbons interchangeable?
Are the carbons interchangeable? What do you mean?
Like, if you have like 6 carbons, could you swap 2 and 5?
You could.
Oh, would that change anything?
So the best way to look at this is, if the formula is the same and the IUPAC name is the same, it's the same thing. And that's why we use IUPAC, is it's one way to unambiguously say, no matter how I draw it, it's one molecule. Does anybody know the IUPAC name of this guy? This would be called what? Right, the guy in red, I would call this hexane, 6 carbons. In green, that is same name, same molecule, different pictures of the same compound. Right. So, look at these. What are these guys now in that same compound? Start with their content, look at their bonding. What do you think these guys would be? And again, take a second. Turn to the person next to you. Convince them of your standpoint. When you form the thing in your mind, why are you right? Okay. So let's see if we have consensus. What is everybody's answer? On 3, the answer is A, B, C, D, E. It is? B. B, I agree with B. That's correct. Okay, let's take them one at a time. First, if they are isomers of heptane. What does that mean? What am I decoding with that? Yeah.
There are 7 carbons.
Well, there are 7 carbons, but more importantly, there's more than just 7 in both of them, right? What does it mean isomers of heptane means what more than just 7 carbons?
Oh, 7 carbons are then in different regions.
More than just that. 7 carbons to be an isomer of heptane, yeah.
They have the exact same.
No, I wouldn't work it that way. What else?
No branching?
Not even. More importantly, we saw the last one, these guys, were both what? The name of the molecule is hexane. One of the ways to look at it is, like here, I have 1, 2, 3, 4, 5, 6, 7 carbons, right? What does hept mean? Let's go back to that. 7 carbons, right? So I've got 7, but the molecule has 8. So sorry, revise. What do you mean? Oh no, I thought you had your hand up again. No, I guess, yeah.
I haven't revised. Is it 7 in a chain?
7 in the longest chain. So think of it this way. When we start talking about isomers of heptane, we're saying that the parent, the molecule, what class of family it is, the longest carbon chain is 7. It is a heptane. It might have branches off of it, but that first molecule, you could class it as some kind of heptane. It would be a methyl heptane. The root of the name is heptane. The second one, how many carbons in the longest chain? 1, 2, 3, 4. That's the best I can do. So what would the root of this molecule be? This is pentane. So no, they are not isomers of heptane. One of them would have a root pent, one would have a root hept, but different branching. So I think that one's out. Constitutional isomers, what am I communicating with that? That's the right thing. Constitutional isomers means same formula, different bonding. Yeah, absolutely qualifies. They're both 8 carbons, same number of hydrogens. You're just playing that stick game, right? You're moving around. You're saying these 2 methyl groups are actually oriented with the one in the middle versus the guys in the end. This is something where if you built that molecule in the top, I would physically have to grab my model, break bonds, and move those chunks of the molecule around to form new bonds. Yeah?
So the isomers of the chain only have to have the same parent molecule to be considered isomers?
If you said something like isomer of heptane, we're saying that the branching or what's off of it could be different, but the parent is the same. So if we said, for example, who's filled up their car? You know there's an octane rating on your gas? What that's kind of talking about is what percent or what formulaic number of your gas is made up of something equivalent to octane, an isomer content. It may have other branching, but it's talking about a unit length of chain, because what we're trying to do is bin things of common points. So here, this mentality of saying it is an isomer of heptane, we're saying which of these are substituted 7-membered carbon changes, right? Bottom would be a pent. They are definitely constitutional isomers. What does it mean to be an optical isomer? Does anybody know that terminology yet? These are molecules that are so similar, the only thing that makes them different is mirror image and symmetry. Your left and right hands are a pair of optical isomers. They're so close to each other, the only thing that makes them different is one is a mirror reflection of the other. This is a type of isomerism we're going to get to much a little bit later in the course. But it's talking about a really, really close similarity. So again, if we had to sort of rank these things in familiar relationships, these molecules, both of them, have 8 carbons. They're kind of like distant cousins. They're very different because this one right here, lots of lights branching, versus the guy in the top, nice linear chain, much more stable. Very different personalities. Optical isomers are really, really, really close. They are not optical isomers because they do not have this mirror image symmetry. And again, we'll get to that. Not all the above, not none of the above. So, what about these guys? Okay. So once again, on a count of 3, A, B, C, or D, consensus is? C. I got a little, it's actually C. 2 of them are the same. So, let me show you something. Because this very quickly becomes either a game of twisting, turning, moving the molecule in your head, there's 2 expeditious ways of doing this. Either, if you built one of these molecules as a physical structure, your model, it allows you to twist and turn the molecule quickly. So for those of you guys from this class going forward, if you have a model kit, bring it to class. This can help you as we sort of work through these problems, right? So practice with your model kit is one way to do this part quickly. The second one is naming. And this is why we use IUPAC name, is if you go through and we find the common pieces of them quickly, we can sometimes we can break these things up. So what would I actually do? 2 of them are the same. Starting with this guy over here, this top corner. How many carbons in the longest chain? There are, 1, 2, 3, 4, 5, 6. Okay, let's go to the next one. I'm going to change colors. How many over here into this guy? There are 1, 2, 3, 4, 5, 6. Okay, next one. Down here, we've got, this is getting boring, isn't it? 6, and last one, 1, 2, 3, 4, 5, 6. They are all isomers of, they're substituted hexanes, right? They've got stuff branching off, but they're basically that core. What is branching off in all of them? What are the branches or substituents to your hexane core that's common to all 3? What is the branch? Methyl, and how many?
2.
So they are all what? They're all dimethylhexane. What makes them different? Where those methyl groups are, the count. So we know that they are all something like dimethylhexane. The difference is where those groups are. So starting off, the guy we've indicated in green, I would count this as 1, 2, 3 dimethylhexane. The guy in orange, which way would I start counting? Top down or bottom up? Doesn't matter, right? Because if I started top down, this is 1, 2, 3, 4. From the bottom up, 1, 2, 3, 4. This is looking at the same molecule, and there's no difference in my numbering scheme depending on which direction I go. This is, either way, a 3, 4 dimethylhexane. In blue, what way would I count? Bottom up or top down? Yeah, this one matters. If I started counting top down, I would call it 1, 2, 3, 4, 5. From the bottom up, this is 2, 3, 4. 2, 4, that numbering scheme gives me a lower number count. And remember, IUPAC rule says, pick the direction of your numbering such that your groups have lower numbers. This is just a common point to give you a frame of reference. We're saying it's the same molecule as this 2, 4 here. If I were to flip this over end to end, it's still a 2, 4 dimethylhexane. We're just presenting it differently. So numbering is not based on how it's drawn. It's based on keeping the numbering scoring lowest. That's why here, this is also a 2, 4 dimethylhexane. So 1, 2, 3, 1, 3, 4, and 2, 2, 4s. So your numbering pattern is one way that you can do this. If you're able to ascribe them to IUPAC naming quickly, we're able to identify them the same. So the bottom two, blue and red, are the same molecule, just drawn in different presentations. So this is where we get to this concept. All of IUPAC naming fits under this big umbrella of hydrocarbons. We say that hydrocarbons are carbon-hydrogen molecules that we begin to decorate. This is our basis. And what we have is two general categories: open chain, so linear molecules, and cyclic molecules, molecules that are bent around in circles. Within this category of open ones, we have what are called saturated and unsaturated. Unsaturated just means contain carbon-carbon double bonds or carbon-carbon triple bonds. The cyclic structures, this is where we get the normal cyclic saturated ones, cyclohexanes, cyclopentane. You see the naming changes where this is still ascribing how many carbons. The name cyclo is our denotion that this is now a ring structure made up of 6 carbons. Aromatic compounds are similar to our unsaturated hydrocarbons. They're cyclic structures that also have double bonds in them. More importantly, they actually fall into a category, special stability over here, because the number above double bonds actually create a special kind of stabilization. We'll talk about those ones more late in the course. But the way you think about this tree is we start off and we basically add things to this, right? So in this guy here, what is the formula for this aliphatic hydrocarbon? All right. All together, the answer is? D. D or E? E. You can sort of sit on the line if you just sort of slur it, right? It is E. Most important things to see about this structure. How many carbons in this box right here? There are 4 carbons, right? We have 1, 2, 3, 4. That's like we talked about last time. That is a triple bond, an alkyne, and it is attached to 2 other carbons outside of that. So don't miss this point. So for people that got that wrong, where was your hydrogen mistake? On the double bonded carbon. Right here?
No, on the other.
Ah, right here. How many hydrogens out there? Dos, yes, there are 2. There is 1 right here. So the 2, 1, all the way through here, none. None here, none here, none here. All of these, how many? There's 3 each, so 3 times 3, 9, right? Wait, is that right? 3, 6, 9, 10, 11, 12. Yeah, woo, okay. Cool. So again, this is just practice through the implicit hydrogen rule. So as far as the naming structure goes, oh, sorry, yes?
Sorry, could you go back real fast? So other cyclic compounds, which one has double bonds again?
Oh, so Cyclic compounds right here, we can have, for example, let me draw this. Let me give you a structure. If I had that, what might you call this? So everybody, how many carbons shown here? This is, and it is in a ring, so it is called cyclohexane, right? What would this be called? How many carbons? It's in a ring, so it's definitely going to be called cyclo. And it's not hexane anymore. It is now cyclohexene. So we can have cyclic compounds, single bonds like this. That is still, it's either, right? We can have one double bond in that sort of third category. Where things get special, this is now called what? Cyclo. Well, how many carbons? 6. It's still a ring, cyclo. And we've got 2 double bonds, so you would call it cyclohex. Well, not just ene. How many enes? Yeah, it's a diene, right? 2 double bonds. Still a cyclic compound. This is where things get weird. As soon as I do that, what is this now? This is special. This is an aromatic compound, and again, we'll discuss what qualifies, but cyclic structures with this alternating double, single, that imparts a whole, this is called the ring of power. It creates a certain kind of bonding energy that makes them a whole different behavior, and we cut these guys apart. These are called aromatic compounds. Okay. So our naming schemes. Oh yeah, sorry.
With a cyclohexadiene,
Yeah.
you have to label where the double bonds are, like 1, 3.
We're going to practice some of those points too, but just like methyl substitutions, you need to say what it is. Cyclo means 6. Hex, there are 6, or sorry, cyclo, it's a ring. Hex means there are 6. Diene, there are 2 double bonds, and we're going to have to add some numbers to say where they are, because there's different isomers to that point. Again, think about it this way. All of your naming needs to be specific enough that all I did is put my hands behind my back and mention the word. You should have only one structure you could draw. Yes?
So does that rule only apply to rings, or it will apply to all other?
All things, yeah. This is what we're going to practice through now, is where we put our numbering and how we do our naming allows us to be very specific about what structure we're talking about. So number 1 is our root. How many carbons are involved? So this is where, if we had a numbering sequence like this, 1, 2, 3, 4, in English, 1, 2, 3, 4. French, my 1, 2, 3, 4, right? Does anybody speak Korean? No? I used to when I'm a black belt in Taekwondo. We used to have to do this counting to 4 a lot. I'm not even going to try now. In OChem, we say meth, eth, prop, bute. This is our counting sequence that we use. So you must be able to count to 10, meth all the way to dec. That is something you absolutely need to know. So this numbering sequence is something that allows us to talk about how many carbons are involved. The naming goes, it starts with our parent chain. This is where we find the longest carbon chain in the molecule. And we go through and we say, based on this, if there are 6, we ascribe it to some root name. How many carbons we have? 6 means hex. This is where we can go back to our link and we can add those other parts. So step 1, find your longest carbon chain. That is always what you're going to do. It's the longest uninterrupted carbon chain too. We're not saying, here's a molecule with a ton of branches and what's the number of carbons. It's the longest carbon chain where you can move along the sigma skeleton without jumping to a new part of the molecule. So you count sequentially. Then we add what's called the infix. This is how we describe if there are double bonds, carbon-carbon double bonds in the sequence. And there's really only 3 choices. If there are none, only singles, we call it an alkane, and that's where you get names like hexane, pentane, butane. If there is 1 double bond, it becomes not hexane, but hexene. We change the an part of the naming to the en. If there is a triple bond, we say yne, Y-N-E. So hexyne immediately means I'm dealing with a 6-carbon chain with a triple bond somewhere. As much as I love pointing for selfies, this is all downloadable. So Totally cool. Again, not a problem. You can take pictures of it, but it's definitely better if you download the slides. So, as you go through these points, this is how you get this naming part. We will always keep the suffix E as long as we're talking about a simple alkane. We will modify that, though, depending on other functional groups. So this is how we build up the name of the structure. We're always going to be talking about something of how many carbons in the longest carbon chain, whether or not we have double, single, triple bonds, and what other functional groups are present. This is the whole point, the master table for the functional groups that you must know for this course. So there is this entire list. This is not the entire summation of all functional groups for organic chemistry, but this is the bounds of what we're going to talk about and discuss and examine for this course. So you do need to know all the functional groups shown here. The point is, we've been talking about the category right here in the middle, hydrocarbons. All hydrocarbons will have this ending of E. The difference it changes is ANE, ENE, or YNE, depending on if it is what substitution pattern. But that's the lateral choice we've just done. What we're going to do, though, is we have this, and the reason this matters, the reason that this table matters is it's laid out like this to show priority. Anything above a hydrocarbon on this table here, so these guys going up, we call this increasing priority. In other words, if a molecule has a carboxylic acid and a thiol in that molecule, we will focus on whatever's higher on this chain as the part that's going to be the name, the thing that will change the ending of the molecule. This is how we rank. If there are really complicated molecules with multiple of these in the same one, it can happen. That's why we laid this out in this way, is we're saying if it's higher on this list, it has a higher priority, it is more important, and it will change the end of the name. Where you're really going to see this come in is in cases like this. That's why we've also bracketed out this table to try and highlight something else. Oops, sorry. You notice we've grayed out this part of the table. Here we go. So this part here and this part here, what we're saying is you are only responsible for functional groups shown here where it is not grayed out. In other words, all of these here will only ever change the end of the name. In other words, we're only going to give you molecules where this part of it here takes priority over something else and will change the root of the molecule. Instead of having hexane, if the hexane had a carboxylic acid in it, it would not be called hexane anymore. It is now hexanoic acid. We will only ever have something where you have to follow this rigor point where we're not going to consider these as a secondary branch. We're decreasing the difficulty of the molecule so that these will only ever change the back part of the name. Likewise, these guys down here will only ever change the front of the name. This is in front of it. We would consider these guys substituents. Just like a methyl group comes before hexane. If we're naming it, we don't call it by the ending. If I have a molecule that has a chlorine, a fluorine, a bromine, we call it fluorohexane, chlorohexane. It goes in front of the name, and we remain at saying, these guys down here, halides, are below the list of hydrocarbons. Therefore, a 6-carbon chain that has one halogen in it is still a hexane. It just has a halogen substituent. Yes?
So if something has a group from the very top of the list and the very bottom of the list, do you say them at the same time, or do you just...
So if we had both, and again, we'll practice through one, up at the top of the list changes the end of the molecule. So let me give you an example. The best one I can come up with right now, let's say we do that. How many carbons? This is also Harry Potter, right? 1, 2, 3, 4, 5, 6. So this is what molecule? 6 is hex, and nothing else on it, ane. All right. Now let's change this to I added a carboxylic acid. It is still hex. It is no longer hexane, it is now hexanoic acid. So I go in here, hexanoic acid. So I'm changing the root because of that functional group. Okay. I am now going to add a chlorine right there. It has two functional groups from our list. The carboxylic acid right at the top, that takes priority. That changes the mentality or the naming of this. The personality of the molecule has changed. It is a hexanoic acid. But it's not just any hexanoic acid. This is what? This is a chlorohexanoic acid. Because on our list, chloro comes down here. It's at the bottom of this table. That's why we're not going to change the end of the molecule. We're changing the beginning. That's what being in this category here, this channel, means. Changes the beginning of the name. This here changes the ending of the name. Halogens will always change only the beginning of the name. So this is not just a hexanoic acid. This is a chlorohexanoic acid. It's not just any chlorohexanoic acid. Which chlorohexanoic acid is it? It is. So who says it's 2-chlorohexanoic acid? Good job. This is what? This is what number? 5. Why is it 5? Who's most important? Look at your name. Remember, okay, we're in Old English times, ye olde times. If you're going to go introduce yourself to somebody else, do you walk up and like, hi, my name is Bob? If you're in Old English times, you walk up and, hello, I am Lord Hine of the Hines. Your last name is your power. That's where you get things like, I am Thatcher. I am Smith. I am, your whole business, your identity is here. It's in the ending of the name. So since the end of the name has our big, big priority, numbering goes with that too. Number 1 will always be associated with whatever changed the end of this name. So even though the number of this could be higher, sorry, Mr. Chloro, you lose out. You're just a substituent at the beginning of the name. You're chlorohexanoic acid the second. Does that make sense? Priority, and this is the thing you have to practice through. And again, this is why we have the assessment. These tools and rules are intuitive, but you have to practice through different kinds. Yes?
So, the question earlier, do we have to write 1 for the location of the hydrogen?
So, good question. In this last one, quick question. Do you have to add 5-chloro-1-hexanoic acid? The answer is no. I do not need to add a 1. Why don't I have to add 1 to this name?
It's already got one.
What's that?
Where it's kind of like you don't have to add a 1 if you're like multiplying something.
No, it's not quite that. Is there anywhere else I could put that carboxylic acid? No, it's a chain starter. In other words, I can't move. If I move that carboxylic acid anywhere in this molecule, it's going to radically change this thing's name. And we'll practice an example. I'll show you this. You know what? We're going to totally go off script. We're going to do it. This is 1, 2, 3, 4, 5, 6. Everybody agree? Chlorohexanoic acid, yes? Nothing up my sleeves. And 1, 2, 3. I'm going to put the carboxylic acid over here. All right? So all I did is I kind of, acid. I cut this group off, and I moved it over here, right? So there's still 1, 2, 3, 4, 5, 6. Still 6 carbons, right? What's the longest carbon chain? 5. So what is this? Is it a hexanoic acid? It's a pentanoic acid now. It's from the noble house of pentane now. This is not just a pentanoic acid. What is this? It is a chloropentanoic acid. And further, it's not just a chloropentanoic acid. This is a 5-chloro, but one more. What is this? What is this chunk over here? Yeah, this is now a 5, well, not 5. 1, 2, 3, 4. This is now a 4-chloro. What's the methyl is on carbon? 2-methyl. And pentanoic acid. If a functional group moves over, especially ones that are these high priority chain starting ones, it is no longer a hexanoic acid, so I don't need to put a number 1 on it. The numbering will always start with that group. I always have to start carbon number 1 is this one over here. So it's implicit. It's redundant, basically. There's no reason to give it a number 1 because that doesn't add any more information about this system. Yeah?
Aside from alphabetical, is there any important constituents?
No, just usually when you're writing them out, you show them out alphabetically. They're not shown out numerically. Yeah. Makes sense? This is also what I said before about IUPAC. It is deceptively, it's one of those things that you get sucked into and you're like, wow, this is so much fun. I hope you guys go home tonight, grab any bottle of deodorant, cooking cleaner, whatever, something like that. Look on the back of it and you're going to be suddenly like, I know what that molecule is. I could draw it. So this is how we do our naming. We need to know our root, we need to know our infix, we need to know our suffix. That forms what the basics of the actual molecule is. So like we talked about, hexane versus this guy, this is our hexene, where we've added this. Now that we've started to add this component, where the double bond is can change. So you think about it from this perspective, we need numbers when we must be more specific. I can't just say it's hexene. That could refer to a number of different positions of this double bond. This guy over here, 1,5-hexadiene. We call it 1,5 because that is one specific orientation, because there's more than just that, right? There's different positions of where those double bonds go. There could be, how many others? Give me one other permutation that would have a different name, a constitutional isomer of 1,5-hexadiene. You could call it what? 1,4-hexadiene, 1,3-hexadiene. This number here, they talk about where that double bond starts. So 1,5 is referring to carbon number 1 is where one of the double bonds comes in, and carbon number 2, 3, 4, 5 is where the other double bond comes in. In other words, if one of those bonds was to slide over in the chain starting on carbon 4, it would be now called a 1,4-hexadiene. This is also what leads to the absolute worst joke in all of organic chemistry. Help me, guys. I'm diene. Don't worry. I'm really triene. I know. But okay. So, branches add the terminology YL. They come off of that chain. So in this case, position, carbon number 2, has a single carbon unit that is a branch. What we're saying with the name 2-methyl-hexane is I have a 6-carbon parent chain that has no double bonds and has a 1-carbon substituent that branches off of carbon 2. Right? That is a sequential point. And again, when you go to decode this, what you'll notice is the sequence you talk about here, sorry, I'll come back to this one. When you do this, the order of your naming and drawing does not have to follow how you read the molecule. As you decode this, you usually say, look, I have to find my parent chain, but I need to know what I'm talking about first. What's my functional group? Hexane is only hexane as long as we know that it is just an alkane. The infix, what our double bonds are, it's not just hexane, it is hexene, hexine. Last thing is, what is branching off of it? So you assemble the name even though it's presented left to right. How you read it and how you draw it may be discontinuous, right? It's going to involve different pieces of this as you go through. That's how we break these parts down. The one last thing I want to talk about is this. We've talked about, if I am a 5-carbon chain, based on our counting in organic chemistry, this is what? 5 carbons is? What is 8? What is 6? What is 3? What is 4? Right. We have some branches, or what are called complex branching, that are so common, we need to have a special name ascribed just to them. Methyl is really, really common. You guys are used to that one carbon. Ethyl, no problem. That follows our normal unit, 2 branches. 3 carbons, propyl, also still okay, but notice what happens here. You can have a branch that is made up of 3 carbons, but now you have some ambiguity in how that branch is connected. What I'm showing here, this is saying if I have a long carbon chain here, this is my branch. But if my carbon chain attaches in the middle of 3 carbons, the branch is still made up of 3 carbons, but it is attached to the main chain by way of the second carbon. We call this guy isopropyl. This was an early sort of use of IUPAC where they're like, okay, we have branches that are 3 carbons, but there's clearly 2 different isomers of it. Okay, that's okay, we'll deal with it. Isopropyl is just iso. Let's go to 4. Okay, butyl, again, 4 carbons, that's great. Oh crap, now we've got sec, iso, and tert. As you start getting longer and longer chains, there become different patterns of connectivity that are all isomers of each other. This is branching in the side chain. So the last thing we're going to do, I'm going to show you a couple examples of these things drawn out, but know these ones on site and be able to use these unofficial naming. The reason why is because they come up so common. The most important thing for you to be able to do is use this part. What I mean is, for example, if I have this is our stop sign, this is what? Cyclo. If I did this, what is that group? 3 carbons sticking off of it is called a propyl. Same cyclohexane, but I go 1, 2, 3, 3 carbons sticking off of it. This is not propyl, this is now called isopropyl. This is where we're going to jump off next time. So I'll see you guys on Friday.